Hey there, podcast listeners. Dr. Sheep here. Welcome back to their podcast, episode 27. I am joined by Anonymous Phil.
Hi.
Well, it finally happened. I got everything fixed.
We got a couch.
We got a new couch. The mic's working.
We have a lava lamp.
Yeah, you can't see it. We have a lava lamp behind the camera. Everything's great. We also have a smart light. Unfortunately, we can't tell Google to turn it off because...
Google's dumb?
Well, I don't know if Google's dumb or if I'm just too dumb to figure it out. And the case is, these podcasts are broken down in 3 parts. First, we have some news. Then we have the comments and how our week have been doing. And finally, some more news. Last time, the separate videos of breaking up the podcast did okay. Watch time overall has been down. Views of the normal podcast are low, but the other ones did okay. One did really well, but again, no watch time, so I don't know if it actually did well or not. So we'll try it again for this week, see what happens. Anyways, the first news topic, and for this first part here, I don't know if you've heard about this. Living robots created as scientists turn frog cells into entirely new life forms.
Sounds like some stem cell research.
It is stem cell research. We can fully program. We can make life.
We can make life. We can play God now.
Literally making our own life
We can
forms.
take a frog cell and make a new baby.
Well, I mean, I wouldn't say that. But, I mean, we took frog DNA, or we took a frog stem cell.
And turned it into a human.
No, we programmed it into these collection of cells. They're probably about a little under a millimeter big. And, they can carry small payloads and can be programmed to do specific things. So, this has...
What do you mean? How do you program it?
Well, RNA is just programming.
Yeah, but I get it, but like that's a molecular level. How do you can't like type some computer code, can you?
They literally did.
What?
This was all done with artificial intelligence.
They typed some computer code,
No,
plugged in a USB drive. All right, this is your new function.
Well,
you get my point?
No, but yes, I get your point in that sense. But they literally, some AI figured out how to organize the cells in such a way that they would do this.
Wait. You're just rearranging the cells, or what do you mean?
I don't fully...
See, that's what I'm trying to get at. It's like, alright, so you write some computer code, now how do you insert this information into the DNA? Because the DNA is a molecular level, this is, it's information that's not molecular. It's not like you're going to print out a new DNA cell and new DNA and, like, reinsert it. You get, like a DNA printer or something. Don't think that's a thing.
Then assemble cells and living boss just... The embryos of African frogs, okay. And they began to work together. The skin cells formed a body while... Xenobots. Oh, this is all dead air. I'm just reading.
They don't really say, do they?
Well, the way... Oh, my ear itches. That's disgusting. The way they made it sound is they just collected the cells together.
Okay, they took these frog cells.
And they just functioned together as a new life form, explored their environment, and did things.
Yeah, but how did they control what they did?
They didn't. They just did it.
They're not...
I don't know. They legit say they just did it.
Did what?
They pushed things around. They could carry payloads.
Well, they're probably just moving.
I know they were.
What's the property of a cell, of a living organism, is the ability to move.
I don't know. It doesn't tell you why. They
See,
move.
I don't think we can program them in a sense where we're becoming, you know...
They said these are programmable, though. We could tell these things to do what we want. Now that we have a vessel...
How do you...
It doesn't say. They don't say.
That's what I
read the article. It doesn't say.
That's what I want to know.
Again, though, they just did this. This just happened. They literally took the instructions from a supercomputer, did it, and there we have it.
I mean, I could see maybe if you took a stem cell, right, and you modified it in some way to represent, say, a heart cell. Now, when this cell reproduces and, you know, replicates itself, it'll be turn into a heart eventually. Or you could, you know, turn it into, like, you know, smooth muscle that forms, like, intestinal tracts or whatever. You know, you could start to form different organ systems based off of how the cell is structured. I mean, I don't know the specifics as to the difference between a muscle cell and, you know, like,
skin
cell at a cellular level. Is it all DNA? Or are they, like, structured? Because I think they all have to have, like, you know, the different organelles and all.
I mean, they're structured differently.
Are they?
Muscle cells
but, I mean, they're all
long, and also skin cells replicate really fast. Muscle cells don't.
Yeah, but that's more in the DNA, though. Like, as far as, like, mitochondria, you know, and all the other different...
I mean, I think muscle cells will have more mitochondria.
I suppose. But see, once again, though, that, you know, in your ribosomes and all that, that's all dictated by the DNA. So I think if you modify the DNA, the cell will start to change. And so it's about modifying the DNA so it'll turn into this other type of cell. That's what I want to know. How do you modify the DNA so it can do this different things?
Well, I mean, we have designer babies. I'm sure it's along the same process.
Okay, so how do they go in and modify the DNA? How do you change the DNA? I mean, all right, I know you can change the DNA, you know, with like radiation.
Oh,
but
CRISPR.
How does that work?
So CRISPR is it's a virus. You use a virus to get into the cell,
okay.
And the virus has all the instructions of how to get its piece of RNA, and how to plug that RNA into the DNA of the cell.
And so that it modifies it. Okay, so then how do you modify this virus CRISPR? Like how do you tell this virus what to do?
The virus knows what to do. The virus has its job. Every virus does the same thing. It infiltrates the cell once it's in the shell.
So is there a specific virus that can turn a cell into a heart cell?
No. What we do is we take the bad RNA, the RNA that the virus would use to replicate into more viruses and to possibly kill the cell. We take that RNA and we replace it with our own RNA. And that RNA is what then tells that cell, the new cell, to have whatever characteristics that we want.
And so how do you
bounds.
Go in and put in this new RNA?
I don't know how they do that. I'm sure they because viruses, they reproduce using other cells.
Because I mean,
so
the
I'm sure,
RNA, it's going to be tiny. You know, like, how do you, like, I don't even get, like, how you could be, like, you know, on the dot, alright, you can't trim off too much, you can't trim off too little, you know, you have to be on the, otherwise, you know, because when it goes through and starts mutating itself, you don't want it to mutate the wrong, you know, adenine, thymine, or whatever, you know, you got to make sure you get the right snippet.
Right. I'm not sure in that department, but I know we can use lasers to hold cells in place and hold things in place.
Yeah. I mean, that's how we, you know, make subatomic temperatures, or, no, super critical temperatures or whatever.
I'm assuming we just use lasers to move around the RNA, but I'm also assuming they use, generations of viruses. I mean, viruses change, they mutate, and you can use, and so you try a process of changing the virus,
Mm-hmm.
and then you put it into some cells, and you get it to replicate, and at some point you're going to get the virus that you want that'll work and function and do what you want.
So it's just more trial and error.
It's always been trial and error with biology. Biology is always trial and error. You should know this.
Yeah, but it's also a lot of just observation and prediction. I mean, that's what Darwin and his finches was. Observation. It wasn't trial and error. All right, let's feed these birds this type of seed, and these birds this type of seed, and see if their beaks change. No,
well, I mean,
he
that's
watched
going to
what they
take
ate.
millions of years.
Exactly.
This, though, we can do in a few years, because
Because bacteria can change that.
Yeah, and cells and bacteria can replicate much quicker than birds.
Yes.
Birds. Yeah, so this has a lot of interesting applications.
Yeah. It'll
web-
bring in some new ethical issues and moral dilemmas about
I never thought about that. No one's mentioned it. It's not even mentioned. Because I think what it is, it's still frog DNA.
I mean, yeah, it's still frog, so I think it's still okay. But it's the idea that, all right, once you start doing this to a human, there's some ethical and moral dilemmas that you run into.
But see, they don't use embryonic. They don't use embryonic stem cells. They use adult stem cells.
Yeah.
So it's not necessarily.
Well, that wasn't the moral thing. The moral thing is changing a human's life so it can
But you're not making a new human. You're not trying to make a new human or modify a
yeah.
human.
Okay. As long as you're not modifying the human, that's okay.
You're not. That's not what's happening here. What's happened? Well, yet. This could lean down the road of that kind of stuff. I think what we could see is what they do is to use adult stem cells, skin cells, and muscle cells,
Yes.
and they come together into these little robots, essentially, that can do our bidding.
Mm-hmm.
That's not... technically, it's a new life form, because these could easily grow, evolve, and change,
Mm-hmm.
and reproduce.
Yeah.
Could.
But I mean, I don't know.
And I think I heard one application, if these things could reproduce, all you have to do is sprinkle a little bit into a water supply and infect all these people. And then after a certain amount of time or whatever, somehow using the programming, turn them from passive to wiping out an entire population like that.
Yeah.
Which is terrifying to think about. You have no idea. These micro robots could be swimming around you, and then next day you're dead.
Mm-hmm.
Because they started eating your brain cells.
Yeah. It just seems modifying cells and all that, it just seems like it opens up a new can of worms for diseases and all that,
This also opens up on the contrary, it also can cure a lot of diseases. Now we can tell it, go kill these cancer cells.
Yeah.
Go take out this bacteria. We could maybe use it to get rid of scar tissue. And get rid of scars.
Yeah. Well, didn't we made the joke one time, eventually, 50 years in the future, you can just chop off your arm and regrow a new arm.
Well, yeah, just go buy a new one, yeah.
Or, if you come back from war and you have prosthetic legs, we can regrow you a new pair of legs.
Yeah. We are dangerously close to that.
Well, you don't like your intelligence level? Here, we'll just give you a new head.
Well,
You'll become a whole new
that's
you.
That's the whole ship dilemma.
Yeah, at what point, the ship of Thales, or
or whatever the hell it's called.
How long does it become a new ship or whatever? But see, the same idea applies to humans as well. You know, your cells are constantly changing. Supposedly, after 7 years,
Every atom in your body is different.
yeah. But see, I've also heard that brain cells don't replicate. So all the neurons or whatever that you're born with, they stop reproducing or whatever after age 20. And so you gain no new brain cells. And so your brain is basically the same.
Well, I mean...
It's the vessel that it's within that changes.
It's still going to exchange... it's still going to change atoms out. Because it's going to have to repair DNA, because DNA gets damaged. And as it functions, it's just natural
Yes,
functions.
but some of the atoms will be there forever.
Potentially.
I heard that you do not get new neurons. Meaning the atoms that make up your neurons now will be those same exact atoms that make up your neurons when you're 50, when you're 70, the day you die.
But DNA's constantly being unfolded, refolded, fixed, broken and refixed all the time. I'm sure it gets replaced at some point. That's why it takes 7 years.
Yeah, but I don't know if you get an entire new set of, atoms, so to speak.
I don't think atoms just get locked up in your head. That would...
Why not?
I don't know. Does it seem...
It seems weird to think that you lose atoms in your head.
No, I could see that. Think about it. There's trillions and trillions of atoms that make up your entire body.
Yes.
What's to say that they don't all get replaced?
So where do they go? They can just get flushed out in urine?
Yeah. You get moved to other parts of the body? You poop them out?
You're pooping out cells that made up your brain. That just sounds weird.
Atoms that made up your brain.
Yeah. No, it just sounds weird.
Well, things get worn down and break. You know, free radicals constantly destroy things in your body, and your body has to rebuild that.
Yeah.
Radiation, you're being bombarded with it. It constantly breaks your DNA. You constantly have to fix that.
Yes, but I mean... Alright. Think about like a tree, for example. Or like a TV. Alright. The atoms that make up this TV, those are never going to change. Right? Those atoms are stuck there.
Yep.
Why does that not apply for life?
Because life's constantly changing.
So I think that's more the surface. I don't think the interior changes.
I don't know. I know a tree. Those atoms are locked.
They just get new rings. A tree just gets bigger.
Yeah, those atoms are
those
locked
are locked in.
But those cells die.
Yes, but the atoms are still there. Otherwise, a tree would be hollow.
Well, some trees are.
No, well, that's a disease.
Yeah.
That kills the inside of a tree.
Osmosis also has a tendency to...
Yeah, but that's for, like, water. Osmosis is like the water flowing in and out of a cell to change salinity levels.
Well, maybe not osmosis, but like helium in a balloon. It doesn't stay there. It leaks out eventually.
Yes. Okay.
Maybe
that's a gas.
Yeah, but maybe it's the same concept. Your atoms, they vibrate out of place and they're gone.
Then it won't be a solid then. The definition of a solid is that the atoms are all bound to one another.
Are you really that solid though?
Do you see me souping out across the couch?
Well, your bones though, your bones.
They're solid.
Yeah, your bones aren't. Your bones are alive, but the most part of the bones, the structural part, are not alive.
Okay, so. But still,
you would soup out without bones.
Okay, but you don't see my skin souping out and sagging over my bones. When you lift up your arm, the skin does not sag around your bone.
That's true. But like the cells themselves, though, when the cells are bonded but those cells are like bonded together in ways. They're intertwined. Because you've seen skin cells.
Okay.
They're not just little circles most of the time.
Yes. We put our hand under microscopes before. Yes.
Well, we couldn't see cells.
We couldn't see cells, but we saw some very small things that just made your hand look gross. Like, that's my hand.
I mean, made your hands look gross. I thought it was just like, oh, another day of looking at your hands through a microscope.
I mean, what do you have? Like 22 vision? Where you got like molecular level vision where you can
22? What the
Yeah,
hell?
like an eagle has like 25 or whatever.
25 is bad.
25. Like there's 20/20.
Yeah.
I'm pretty sure an eagle is like 25. What you see at 5 feet away, an eagle can see at 20 feet away.
So no, it'd be.
Is it 5/20?
No, let me.
Whatever the number is.
My right eye is 20/25. My left eye is 20/15. My left eye is like 10 feet better than my right eye.
Okay.
Which actually makes a big difference.
So the number below gets bigger. 20/15. So an eagle is 25, 24, thereabouts.
No. The smaller number, the better.
Yes. No, which one comes first?
The 20 always comes first. Because 20 is the standard. I don't know who made this up. I still don't understand. I asked the eye doctor. He explained. I still didn't understand.
Whatever the case may be, what an eagle sees at 5 feet away, you see at 20 feet. The point I was trying to make is that you were just like another day, another vision, whatever. It's like what? You can see that good every day?
Yep.
That's the joke I was trying to make. No, my point, though, that I was trying to make, though, earlier, is that even though those atoms are molecules, they're stuck there. They're stuck there.
I don't know. I mean,
Think about the Earth gets...
Is it just the DNA, then?
What?
Or is it the DNA and the
What are we
phospholipid
talking
bilayer?
about?
The parts that don't change in let's say, a nerve cell.
So if you have a nerve cell...
A brain cell, neuron, whatever.
So a neuron cell.
What part doesn't change? Is it the phospholipid bilayer?
Or does none of it change? And it just gets energy from electrons?
No. But the cytoplasm changes constantly. And
in what way?
Cytoplasm doesn't... the cytoskeleton.
Cytoskeleton, okay.
Constantly changes. It's constantly reforming and forming. Well, it's gonna throw away cells, and this all consumes energy.
See, I believe you could think about it the same way. I mean, think about it this way. Okay.
But
we are a collection of cells, okay? Now, if you think about one cell, one individual cell, I don't think every single atom within an individual cell changes.
Well, like I said, I don't think the phospholipid bilayer and the DNA and the phospholipid bilayer that makes up the nucleus membrane change. I could see those not changing, but everything else, easily I could see changing.
I could see, like, the outside molecule, See, here's the deal. When you break a molecule, it becomes something new.
Yeah, something unstable.
Exactly. So you can't change the inside. So if you have a molecular structure, you can't change that inside carbon atom because it becomes something new if you removed it and broke it up.
Well, yeah. If you break that molecule, though,
so you can't.
It becomes waste.
Yeah,
typically, and the cell get rid of it and will replace it with something new.
But now you're ruining the structure, though. So I believe what happens. I believe it's just.
But that happens. That's age.
Yes, but I believe it's more or less just electrons being exchanged. And you're just adding new molecule chains on, and it gets bigger.
I just realized I'm wearing my lab coat.
Yeah? No, but that's what I'm trying to say. I think it's just electrons being exchanged. I don't think you lose... I don't know if you really lose any atoms in your body. I mean, other than, like, liquids. But...
And your skin.
Sure. like it sheds off
And all the
because
dead
of
red blood
because
cells,
of weak hydrogen bonding or whatever.
all
it
the
is.
white blood cells.
But those are cells. I'm talking about the molecular components of a cell.
No muscle cells. Any cell that dies and reproduces, those.
But the cell disappears.
True. Well, there's only
And actually, I
brain
actually
cells
heard that you
and
actually.
nerve cells stick around.
I actually heard that you actually don't get new muscle cells. So when you work out or whatever, you don't get new muscle cells. What happens is the muscles get bigger. The cells get bigger and more spaced out.
Yeah, but you can tear a muscle and it will regrow. You can't tear a brain and regrow it.
No. When you tear a muscle cell, you're tearing the fibers. And when it regrows, I don't know what's happening at the molecular level, but I heard in one of my biochemistry classes that you don't get new cells in that process. The cells get bigger, and the bonds that hold them together get stronger, the bonds, but you don't get new cells.
I'm talking about like damage, like a knife cutting your arm.
Yes.
Damage. I'm not talking working out because that actually doesn't cause damage. That
No,
just makes them bigger.
it calls microfibers tear, microscopic tears.
See, that's what you're always told. See, I don't know I don't think we actually even know because I've heard other sources where that's wrong.
What?
Yeah, I've heard there aren't.
Because every single biology class I've ever taken says that when you work out, you cause microscopic tears in your muscles. Then you have things called satellite cells that come in and they repair the cell.
Yeah, that's what we're told. But like, I'm pretty sure with SciShow it says that's not true. We actually don't really know what happens. Something like that happens, but that's not actually how you get stronger though, quote unquote. This was SciShow.
Yeah, I don't know.
We've gone down a rabbit hole here.
Yeah, but I mean, at the molecular level, I don't think you can truly. I think it's more or less a theory. Everyone has their own theory, but I mean, like, we can't like put a microscope up to your arm and like watch what's happening as your muscle changes because it takes forever.
That's always a question. You know, I've seen videos
So I
of
think
like
it's all theory.
blood moving through blood vessels.
Yeah.
I'm like, how did they get that?
Well, I mean, we have. Oh, I guess I was thinking more like. We can actually have video of light moving through a bottle. I mean, I guess I was thinking about it in terms of like slow speed, but you're talking about like just the super small. No, there's this TED Talk or whatever. Oh, they call it the femtosecond camera, because what it is that you can literally see a pulse of light travel through the bottle, and so then you get the question, well, how? Because if it's a camera and the camera's shooting light and it's taking frames, how can you get a picture of light moving? If light all travels at the same speed? Well, the answer is that you're taking multiple frames. It's a continuous process of shining light through a bottle over several minutes. But the action is that they made this camera that can take a super quick picture or whatever. They engineered it or whatever in such a way to have these short frames. So they send a pulse of light, take a picture, send a pulse of light, and then it's like one of those like flip books that when you play it back, you can see a pulse of light here, here.
Oh, so it's like taking so like the light, say like the light's like a car driving by, and like these like each.
You take a picture when the light's here. You take a picture when the light's here. You take a picture when the light's here.
Well, yeah, that's how a camera works. But I mean. It was multiple pulses of light, right?
Yes.
Yeah, oh, okay. But it only did it once. It's not like it can do it multiple times. It took a shot, and then they had to do it again, and it took another shot. Yeah. Okay,
But the point is that they made the exposure time that quick. Because it took a lot of synchronization.
That's crazy you could even do that. I mean, how did
It took a lot of synchronization to
How do you get the electrons to move through the sensor that fast?
It's some new technology they made. But see, what's crazy about this is that...
Unless it was superconductive.
But what's crazy about this is that they showed that you can actually use this technology to show, like, invisible things. So say you have a person behind a wall, right? If you take a picture, if you shine this light, right, when light hits the wall, it bounces back. When light hits the wall, it doesn't just bounce straight back. It reflects off and bounces back. So some light comes here, bounces off the wall, bounces off whatever object is behind the wall, penetrates off the wall and comes back. So they used this immense program and the synchronization to actually program what was behind the wall. So they took an object, put it behind a wall, and they were actually able to make a computer-generated image of the object behind the wall based off of the light that was bouncing off of it.
That's the same sort of
It's
line
crazy.
where they have. That's the same kind.
So it's like if you're like you could have this military technology where you could see if there was a guy behind. I mean, I don't know how long it'd take for this process.
I'm like,
But you
you're
could have
gonna
like a
need
team.
really
But if there was
powerful.
a team of army soldiers right here, like snipers behind a wall, and you took out this camera before you, and you could just see, all right, we got 5 guys right here. Let's shoot our guy, you know.
I mean
that's the kind of thing that's a hint to that. But I mean, I don't know all the specifics as to how this all worked. They just explained it. They just explained the process of how it does work. The idea that light's bouncing off the object, coming back to the camera, and through this program that they wrote, they're able to use the light and the information they got back in the shadows. Because I imagine there's different light intensities that came back, you know. Because light that comes directly off the wall is going to be more intense than light that took several bounces. And they're able to use that from the program.
Well, that defeats the purpose of making things invisible technology and nanofibers.
No, so then you just need to make something that absorbs light, like use an immense black body or something, so the light that bounces off never bounces off.
I mean, we're working on that.
So that way, no light goes back.
I mean, we have that's the our stealth bombers.
No, because see, then you create an invisible image. It'd be like creating like a hole in the picture. So the light that would bounce above your head would come back. The light that would bounce around your arms would come back. The light that would bounce between your legs would come back. And so it'd just be like this wall with like this empty negative space of where you are.
Okay, should we what time are we at? Is that 30 minutes? Oh my gosh.
34 minutes.
Okay, that's enough of that.